Good morning, students. In this video, I am going to explain about the remaining registers in the register organization of 8086 microprocessor. Remaining two classes are there that we have to discuss in this class. As we know, the 8086 microprocessor, internally it is having the 14 16-bit registers, because 8086 microprocessor is a 16-bit processor. It processes the data, it handles the instructions with 16-bit, so that 8086 microprocessor is a 16-bit microprocessor. It has 14 16-bit registers, and all these 14 16-bit registers are classified into 5: general purpose registers, segment registers, index registers, pointer registers, and the flag register. Total 5 classes. With these 5, we can have all the 14 registers. In the previous classes, we have discussed about the 3 classes, 3 types of registers, that is general purpose, segment registers, and the index registers we have discussed. In this class, we have to discuss about the remaining two types of registers in the register organization of 8086 microprocessor. First one is a pointer registers we have to discuss. Another one is flag registers we have to discuss. With this, the register organization of 8086 microprocessor with the 14 registers will be completed. And this register organization of 8086 microprocessor will be directly asked for 10 marks in the exam. The 2 possible questions from the first unit is that, so far whatever we discussed, first one is architecture of 8086 microprocessor. The last one is, second one is register organization. One more thing we can expect the long answer question in coming class. I am going to explain that one, that is addressing modes of 8086 microprocessor. Then coming to the 4th type of registers in the register organization of 8086 microprocessor, that is called pointer registers. There are 3 registers are there in the pointer registers. First one is stock pointer register, instruction pointer register, and the next one is base pointer registers. All these combinedly named as pointer registers. These 2, stock pointer register and instruction pointer registers, are used to hold the offset address of a memory location. In the last classes, I have explained what is the offset address in the outside of the memory and what is the necessity of offset address to generate the physical address we have explained. So, I am revising that topic in short, that is 8086 microprocessor can be accessible with the 1 megabyte of memory, but at a time, in a given time, it can't access with the total 1 megabyte of memory, so that memory will be divided into 4 segments. First segment is extra segment, data segment, code segment, and stack segment. These are the 4 segments. Each segment is 64 kilobyte. And that location, each segment locations will be indicated with 20-bit address. Whereas 8086 microprocessor internally, that is storing the 16-bit address only, but the outside we can identify any address location in the memory with the 20 bits. So that we can have this 20-bit address by using the one formula which involves the segment address and offset address. Segment address is stored, 16-bit segment address is stored in the segment registers. That is second class of the register organization, second type of register organization. And in order to generate the 20-bit physical address, we require to have the offset address that has to stored internally in the microprocessor. 16-bit offset address has to stored. That means what? 4 segment address. So 4 16-bit segment address are stored in the segment register. 4 16-bit offset address has to be stored in the 8086 microprocessor. 4 16-bit offset address. 2 are stored in the index registers. That is source index register. Source index register is to store the offset address of data segment. Offset address, that is offset address of data segment. Then destination index register is used to store the offset address of extra segment. Data segment is completed, extra segment is completed. Offset address of data segment is stored. Offset address of data segment is stored in the source index, whereas extra segment is in the destination index registers. But we are having the 2 more segments. One is code segment, another one is stack segment. The offset address of stack segment register, offset address, that is 16-bit offset address of a stack segment will be stored in the stack pointer register. That means what? The starting 16-bit address of a stack segment. We are having the 4 segments in the 1 megabyte of memory. In the stack segment is one of that one, and the starting address of that stack segment will be stored. Starting address of offset address of that stack segment will be stored in the stack pointer register. So that in the segment registers, in the stack segment registers, we are having that segment address, and here the stack pointer which is holding the offset address. By using this segment address and the offset address, we can generate the physical address of a required memory location in the segment, in the stack segment. I hope I am clear. That is what? Here the stack pointer is a 16-bit register which holds the offset address of a starting address. Offset address, that is nothing but starting address of offset address of a stack segment. And coming to here, that is instruction pointer. Except from the 4 segments, 3 completed. One is a data segment is completed, extra segment is completed. With this, stack segment is also completed. We left with only 1 segment, that is code segment. Code segment, code is nothing but instruction. That means what? It is a segment in which the processor, from that the processor can fetch the instructions, or the processor can write the instructions into that segment. So that it is named as code segment. So that this instruction pointer, instruction is nothing but code only. Instruction pointer is an internal 16-bit register of a 8086 microprocessor, which holds the offset address, of a code segment. Offset address of a code segment. Offset address means column address. Obviously, this instruction pointer is holding the offset address of code segment, whereas code segment register is having the segment address of that code segment. And this offset address and that segment address combinedly generate the 20-bit of physical address. In the last class we have discussed. Coming to the base pointer register. Base pointer register is going to give the accessing of stack memory. Stack memory, we are having the 4 segments. What are the 4 segments we have? Data segment, extra segment, code segment and stack segment, which will give the accessible for the stack memory. Stack memory, whatever the stack memory is there, based on this register we can access that stack memory, and these three comes under pointer register. These 3 are what? Pointer register. Stack pointer, this which holds the offset address of a stack segment, And here instruction pointer which holds the offset address of a code segment. Last one, base pointer register, which base pointer register can be used as the base register for the accessing of stack memory. Just now I have explained. It is acting as a base register. It is acting as a base register for accessing the stack memory. We know the stack memory is about 64 kilobyte in the external memory. That is about 20-bit address. Each location is having identified by the 20-bit address. The maximum of it is having 1 megabyte of memory. The memory locations will be identified by the 20-bit address, so that it starts from 5 zeros to 5FH. So here this is about the pointer registers. And now I am going with the last type of registers in the register organization. That means what? We have the 5 types of registers in the register organization. General purpose registers, it is having the 4: AX, BX, CX, DX. And again segment registers, we have discussed the 4. That is what? Segmented data segment, extra segment, code segment, and the stack segment. 4 plus 4, that is 8 completed. Now we completed 3, so that 11 completed. Now we are going with the 8 plus this is 3, 11, and we have discussed the 2 more register, that is index register, that is source index register, and the destination index. 11 plus 2, that is 13, and this one is the last register, that is the 14th register. One of the important feature of 8086 microprocessor is that the 8086 microprocessor is having the 14 16-bit register. It is having the 14 16-bit registers. It is having the 14 16-bit registers with the 4 registers, the 13 completed, and the last register we have to discuss, that is flag register. Flag register, the function of flag register is nothing but it is going to give the status after executing some instruction. The processor or the CPU is going to give the status by making use of some flags. Flag is nothing but here what? Flag is nothing but it is a flip-flop. Flip-flop, it can able to provide the 2 states only, 1 and 0. 1 is called as set, 0 is called as reset. We know this one. That means what? After executing some instruction, these by seeing these flags, we can have the status of that particular function of the 8086 microprocessor. Here it is a flag register, only one flag register is there. That flag register is used to indicate the status of execution, status of CPU after executing instruction. It also provides some control flags also. So that here we are going with the flag register, and we know that the 8086 microprocessor is having 14 16-bit register, so that it is a 16-bit register. 0 to 15 means it is 16-bit. It is having the 16 flags. Flag is nothing but it is a flip-flop which can provide, which can indicate, which can give the 0 or 1. So that these out of 16, 7 flags are undefined. These are kept for the future use. That means what? It is a 16-bit register. 0 to 15, 16, and in which 7 flags are undefined. 7 flags are undefined, which are marked with, or which are identified by the, which are represented with the crash mark, and these are undefined, which are kept for the future use. Out of 16, 7 are undefined, so that remaining 9 can be classified into 2 things, that is conditional flags and control flags. Out of 16 flags, Out of 16 flags, we have 7 are undefined, remaining 9 are divided into conditional flags and control flag. Condition flags are 6, whereas control flags are 3. These 3 are control flag. Direct flag, direction flag, that is interrupt flag, and next one is trap flag. These 3 combinedly named as control flag. These 3 combinedly named as control flag, and remaining 6 are named as conditional flags. I am very clear that the flag register internally, the 8086 microprocessor is having one flag register which is 16-bit wide, in which each flag represent either the status of the after the execution of any instruction, or it can give the control signal. It can give the indication of the control signal. 2 things it can describe. It can indicate, one is the status after execution the instruction, and second one, it is going to give the indication of some control signals. And out of the 16 bits, 7 bits are undefined, which are kept for the future use, and remaining 9 are classified into 2 types. One is conditional flag, another one is control flag. And in conditional flag we have the 6 flags, and whereas in control flag we are having the 3 flag. And in control flag, what are the 3 flags? Which one is a trap flag, interrupt flag, and a directing flag. Remaining 6, what are the remaining 6? First one is carry flag, next one is parity flag, next one is auxiliary carry flag, next one is zero flag, and the 1, 2, 3, 4 completed, and the next one is about overflow flag. This is about sign flag. Last one is about sign flag. Then how this is going to give? Carry flag. That means what? In the processor, if it is performing addition or subtraction, if there is a carry, then this flag is set to 1. Then that flag is set to 1. Otherwise, it will be reset, that is 0 in case of addition. In case of subtraction, if there is a borrow to perform the subtraction, then that will be set to 1, otherwise it will be a 0. So that I am repeating the statement. It is set whenever a carry or borrow occurs during the arithmetic operations such as addition and subtraction. Otherwise it's set to 0. If we get the carry in case of addition, that's set to 1. If we get the if we require a borrow to accomplish a subtraction, this will be set to 1. Otherwise, it will be 0. That is carry flag. Next one is the zero flag. Next one I am going with the zero flag. It is set to 1 whenever the arithmetic and logical operation is 0. Mostly this will not be possible. If you are going with addition or subtraction, if you get the result is 0, if you are getting the result is 0, that will set to 1. Otherwise it set to it reset to 0. That clear it is? It is set to 1. It is set to 1 whenever the result of arithmetic and logical operation is 0. That is called, it is a zero flag. Carry flag is what? In the addition or subtraction, if you require a borrow in a subtraction, if you get a carry, then this will be set to 1, otherwise 0. And coming to the zero flag, if the result is 0, then that's set to 1, otherwise it is reset to 0. Then auxiliary carry. That means what? Whenever we are performing addition, BCD addition or BCD subtraction, bit 3, that means what? B0, B1, B2, B3, up to we can have up to B5. B0 to B5, it is 16 bits, so that whenever the B3 will provide the carry to the B4, or in the subtraction, whenever B3 require a borrow from the B4, then that set to 1, otherwise it will be 0 or it will be reset to 0. I hope I am clear in case of auxiliary carry. In case of auxiliary carry, whenever we are performing the BCD addition, in the BCD addition or BCD subtraction, B3 generates the carry to the B4, or B4 will give the B3 requires a borrow from B4, then this auxiliary carry set to 1, otherwise it reset to 0. Then parity flag. Next one is about parity flag. That means what? Counting the number of ones in the counting the number of ones in the result. When the in the result, when the number of ones are even, then this set to 1, otherwise it reset to 0. That parity flag is nothing but the counting number of ones, counting the number of ones in the result. In the result, the number of ones are even. In the number of ones are even, then that set to 1. Otherwise, if the number of ones are odd, then that set to the reset to the 0. Then that is about parity flag. Then sign flag. Sign flag is nothing but when the arithmetic logical operation is negative, when it is negative, then that is set to 1, otherwise it is 0. If you get the result is in negative, then that set to 1, otherwise it set to 0. Most of the cases it set to it reset to 0 only. It is 0. Sign flag is most probably that is 0 only. We cannot get the negative numbers in the binary case. So that next one is overflow flag. Now overflow flag is nothing but whenever in the addition of the two 16-bit numbers, this flag is set to 1 whenever there is a carry into the MSB. Then that's set to 1, otherwise it's set to 0. And if it is no carry to the MSB bit is what? It is a 16th bit. It is a 16th bit or it is a B15. Whenever it is getting the carry, then that is overflow, that's set to 1, otherwise it's set to 0. In subtraction, whenever MSB needs a borrow from the another 16-bit number, then that's set to 1, otherwise it's set to 0. This is about all the flag registers. I am going to in the flag register, that is conditional flags we have discussed. After that we have to discuss the control flags. I am going to explain this carry flag. Carry flag is what? Carry flag is what? Whenever in the addition it generates the carry, then it sets to 1, otherwise it sets to 0. In the addition, if there is a carry, then that will be set to 1, otherwise it set to 0. Parity is that if the number of ones in the results are even, that set to 1, otherwise it is 0. In the auxiliary carry means what? In the BCD addition and BCD subtraction, if B3 bit generates the carry to the B4, set to 1. In case of subtraction, B3 requires the borrow from B4, set to 1, otherwise it is 0. 0 flag is what? If the result is total in the arithmetic and logical operations, if the result is 0, that set to 1, otherwise it is 0. Sign flag is nothing but mostly this can be used for signed binary numbers. But if you get the result is in negative, that will be sign is about 0 and sign is 1, otherwise it will be 0. Overflow is nothing but what? Overflow in case of BCD, in case of addition, if the MSB give the carry to the next 16-bit number, then they set to 1. In case of subtraction, MSB require a borrow from next 16-bit number, then that set to 1, otherwise it reset to 0. This is about all the flags. And coming to the remaining 3 flags that are control flags, whatever the 6 flags we have discussed, that comes under conditional flags. Now we are going with the control flags. Control flags are 3, that is first one is directing flag, next one is interrupting flag, next one is trap flag. Here interrupt flag. Interrupt flag is nothing but interrupt flag. IF is nothing but interrupt flag. Flag is nothing but it is a flip-flop which can provide either 0 or 1. Flag, interrupt flag, whenever the non-maskable interrupt and the maskable interrupt will interrupt, whenever that signal will interrupt the 8086 microprocessor, this after serving that instruction, after serving that interrupt, this is going to give the indication that is 1. Whenever it interrupted and whenever it is serving, and that indicates with 1. Otherwise, if it is not getting interrupted by any other interrupt signal, that may be non-maskable interrupt and the maskable interrupt, otherwise it's set to 0. Then TF is nothing but what? It is a trap flag. Whenever trap flag is set to 1, it enters into a single step mode. It enters into a single step mode where the processor is going to identify, where the processor is going to search for the errors in the instructions. Here, whenever the TF is set to 1, that is a trap flag is set to 1, the processor enters into the single step mode so that this processor is going to search for the errors in the given instruction. Next one is about directing flag, that is DF. Whenever it's set to 1, it access the higher address to, it access from higher address to lower address from the instruction or data, and whenever it's set to 0, it can access the lower address to higher address to access the data or instructions. These 3 are combinedly named as control flags. Remaining 6 are conditional flag. Out of 16, 3 plus 6 is 9, and remaining 7 indicated with the cross mark, and these are undefined flags which can be used for a future purpose. Then based on this information, we are going to solve the one particular problem to represent all the flags, and the flags in one example. I am going with one example. I am going with the addition, BCD addition. I am going with the addition. I am going with the addition, that is 0110, it is 2, 0101, it is 5, 1101, 13, and 13 is nothing but it is C, and 0001. Next one is I am going with 0010, 0011, 0010, 0010, and the next one is 1010. I am going to add this one, BCD addition I am going with, such that we have to find out what is carry flag, what is parity flag, what is auxiliary flag, what is zero flag, what is sign flag, and what is overflow flag. These are conditional flags. So that add this 1 1 0 1 1 1 1 1 1 1 1 0 0 0 0 and 1. This is the answer, in which we have to first count with carry flag. Carry flag, that means what? Whenever the result, whenever this is giving the carry to the next 16 bit, then only it's set to 1, otherwise it's set to 0. And here this is a 16-bit number, this is also 16-bit number. We are adding two 16-bit numbers, so that result also 16-bit. There is no carry. There is no carry means there is no carry. If it get the carry, that will be the 17-bit number, but here there is no carry. We are adding 16-bit to 16-bit, we are getting the result also 16-bit. No additional bit has came, so that no carry. So that no carry means it's set to 0. CF is equals to 0. If there is a carry, that's set to 1. If there is no carry, then that reset to 0. Then coming to the parity flag. Parity flag is nothing but what? By counting the number of ones in the result. By counting the number of ones in the result. By counting the number of ones in the result. By counting the number of ones in the results, we have to go with the parity flag. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If the number of ones are even, then that's set to 1, otherwise it reset to 0. That means what? Here, this is right only, this is right. Then, here what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is a odd number, so that this parity bit PF is reset to 0. That means what? If the number of ones are even, that's set to 1, otherwise it reset to 0. Then auxiliary carry is about B3. If this addition of two B3 numbers will give the carry to the B4, then that will be set to 1, otherwise it reset to 0. That means what? 0 plus 1, 1 only, it is not giving any carry to the B4. So that auxiliary carry flag is also, that is 0. Next one is about 0 flag. The result is not 0, so that it's set to 1. The result is not 0. Result, if the result is 0, if the result is 0, that is set to 1, then otherwise it's set to 0. That means what? If the result is set to 0, then that will be set 1, otherwise it is 0 again. Then coming to the next one is a sign flag. It is a positive number only, and so that sign flag is also 0. And the last one is overflow. Overflow is nothing but, then if there is a carry, for M3, then that is set to 1, otherwise it's set to 0. That means what? Here there is a carry for MSB, so that it's set to 1. That is nothing but what? It is a overflow flag. OF is equals to 1. Like that, you can go with the status, the conditional flags of status after executing some of the instructions, and you can take the subtraction also. In the subtraction also, you can able to find out what is the status of carry flag, parity flag, auxiliary flag, 0 flag, sign flag, and the overflow flag. These 6 are combined in named as conditional flag, whereas these 3 are called control flag. With this, register organization of 8086 microprocessor is completed. The register organization of 8086 microprocessor, we have to explain the 14, 16-bit of registers. We have to actually explain the 14, 16-bit of registers, and these 14 number registers will be classified into 5 general purpose registers, that are AX, BX, CX, DX. And the next one is a segment register, which are 4 again: data segment, extra segment, code segment, and the stack segment. And the 4 plus 4, 8 is completed. Next one is the index register, that is source index register and destination index register. These are 2, so that 4 plus 4 plus 2, 10 completed. Next one is pointer register. There are 3 pointer registers: the stack pointer, then the instruction pointer, and the base pointer. And the 4 plus 4 plus 2 plus 3, that is 11. And the last one is a flag register. It is a single register which is a 16-bit wide, in which the 7 flags are undefined, which kept for the future use, whereas the remaining 9 can be categorized into 2 things, that is conditional, which are 6, and the last one is a control flags. With this, 8086 microprocessor register organization is completed. We can expect one long answer question from this 8086 microprocessor register organization. In tomorrow class, I am going to explain the addressing modes of 8086 microprocessor with the 2-3 classes. With the 2-3 classes, the first unit is going to complete it, so that if you have any queries in the first unit, you can post the queries in my mail. Anyway, I am going to share my mail in the description. Thank you.